Solid-state batteries? A revolution that arrived late? Or one that's finally here? For electric vehicle owners, there are three biggest fears: turning on the heater in winter and watching the driving range drop by half, reading news about battery fires and feeling uneasy, and hearing that a new breakthrough technology is coming, yet never seeing it mass-produced. Solid-state batteries, the so-called next-generation technology that has been talked about for more than a decade, have recently shown real signs of progress. And this time, the key variable comes from China: the physical sealing of liquid batteries. Today's electric vehicles are, in essence, still based on a technological framework from the 1990s. Lithium ions move through a liquid electrolyte like fish swimming in water. This design has been used for over 30 years, and it is now hitting its physical limits. Energy density is approaching its theoretical maximum. To achieve longer range, manufacturers have to stack more batteries, but the added weight reduces efficiency. Safety is an even bigger issue. Liquid electrolytes are flammable. Once the separator is damaged and the positive and negative electrodes make contact, thermal runaway becomes almost inevitable. Nearly all EV fire incidents can be traced back to this fundamental problem. The idea behind solid-state batteries is straightforward. Replace the liquid with a solid. No burning, no leaking, and theoretically double the energy density enough to support ranges of over 1,000 kilometers. So why, after all these years, can't you buy one at a dealership? The underestimated engineering challenges. As early as the 1830s, Michael Faraday discovered that certain solids could conduct electricity, but turning a laboratory sample into a mass-produced product involves a massive engineering gap. The core issue is contact. Liquids naturally wet and fully coat solid surfaces, but when two solid materials are pressed together, microscopic gaps always remain. These gaps cause resistance to spike, severely degrading battery performance. The industry has tried brute force solutions, applying extreme pressure, hundreds of atmospheres of pressure, compressing battery components like a hydraulic press. But this creates new problems. Maintaining such pressure requires heavy mechanical structures, which are impractical for vehicles. Material costs are another obstacle. In the mainstream sulfide-based approach, the key raw material, lithium sulfide, has cost thousands of dollars per kilogram, and it releases toxic gases when exposed to moisture. This is why solid-state batteries have remained stuck in the concept stage for so long. Either the performance falls short, or the cost is astronomical, or mass production is simply infeasible. A new variable at the materials level. In January 2025, a research team led by Professor Ma Cheng at the University of Science and Technology of China, USTC, published a study that introduced a different technological path. They developed a lithium, zirconium, aluminum, chlorine oxygen solid electrolyte whose key characteristic is that it is soft. On a microscopic level, it can deform slightly, allowing it to make tight contact with electrodes under only about 5 megapascals of pressure. This is comparable to the packaging pressure used in current liquid batteries, meaning no production line overhaul is required and no hydraulic press needs to be installed in the vehicle. More importantly, the cost structure changes dramatically. The core raw material shifts from expensive lithium sulfide to inexpensive zirconium tetrachloride. According to the paper, raw material costs drop to less than 5% of traditional solutions. This is not incremental improvement, it is a path switch, using low-cost materials to meet high-performance requirements. The industrial timeline. A technological breakthrough is only the first step. What the market really cares about is the mass production timeline. CATL, the world's largest power battery manufacturer, has officially stated that 2027 is the target for small batch production of all solid-state batteries. The company currently rates its technology readiness at 4 out of 9, aiming to reach 7-8 by 2027. At the same time, CATL is already mass-producing semi-solid condensed batteries with an energy density of 500 watt-hours per kilogram, targeting the high-end market first. This two-step strategy is highly pragmatic. Rapidly commercialize semi-solid products using existing production lines, while stockpiling full solid-state technology ready to scale up once the cost curve becomes favorable. In the US, QuantumScape represents a more aggressive approach, pursuing an anode-free design that has entered B-sample testing with automakers. Their bottlenecks lie in production speed and yield, and they are deploying new heat treatment processes in an attempt to break through. In Europe, some interesting edge innovations are emerging. Certain startups bypass the strict automotive certification process and deploy solid-state batteries, first in electric aviation, drones, and high-performance motorcycles, trading use cases for time. The key question: cost and scale. One rule of technological history is clear. The adoption of disruptive technologies depends not on laboratory performance, but on cost curves and production scale. USTC's materials breakthrough addresses exactly these two dimensions. If raw material costs can truly be reduced to 5% and remain compatible with existing production lines, the path to mass production may be much shorter than expected. That said, this is still only a possibility. Between a published paper and factory-scale production lie many hurdles: process validation, supply chain construction, safety certification, and market acceptance. For now, the most optimistic industry forecast is small batch production by 2027 and mainstream adoption around 2030. What does this mean for you? If you are planning to buy an electric vehicle today, there is no need to wait for solid-state batteries. Liquid battery technology still has a 5 to 7 year window for iteration, with continuously declining costs. But if you follow technology trends, the next 3 years are worth watching closely. Once solid-state batteries break through, the impact will go far beyond electric vehicles. Smartphone battery life, electric aviation, home energy storage, and power grid load balancing will all benefit. The endgame of this race is unlikely to be a single dominant technology. Instead, different scenarios will diverge. Full solid-state batteries for high-end vehicles, semi-solid batteries for mainstream cars, condensed batteries for consumer electronics, each finding its own balance between cost and performance. And China's role in the global battery industry is shifting from a manufacturing hub to a source of innovation. That may be the most important long-term variable of all.